This is the 28th lecture on DSP, and the topic for today's lectures are digital filter structures. The last lecture, that is 27, was a problem solving session, and before that we had discussed analog frequency transformation, and the problem was to transform a normalized low pass filter with normalization like this. The omega p was taken as 1, this is 1 delta p, and then the tolerance delta s, and this frequency, the stop bend edge, is omega s. This is to be transformed to denormalized if it is low pass, and the complex frequency variable in normalized low pass is capital S, then capital S is to be replaced by small s divided by omega p. In denormalized high pass, the transformation is simply the reciprocal of this, omega p by s. In band pass, the transformation is capital S equal to s squared plus omega naught squared divided by b s, where b is omega p2 minus omega p1, and omega naught squared is equal to omega p1 omega p2, and that should also be equal to omega s1 omega s2. If it does not happen with the given specs, then you shall have to alter omega s1 or omega s2. Okay? You can alter both, but that is risky, because if you under satisfy one of the stop bends, then the design is not acceptable. Your pass band is sacred, you have to satisfy this exactly. Stop band can be taken liberty only in one direction, you can over satisfy, not under satisfy. In a similar manner, if it is a band stop filter, then capital S is equal to B s divided by s squared plus omega naught squared, and here also the B has no physical significance now. It was the bandwidth in the band pass case, but it is the same omega p2 minus omega p1. This is not the bandwidth. The pass band width is 0 to omega p1 on the lower side and omega p2 to infinity on the higher side. The stop bandwidth is omega s2 minus omega s1, because this is a band stop filter. This is one of the important points to remember. Then we discussed digital filter. We had started discussion on digital filter structures, and we considered the problem of analysis. Analysis is very simple. One can write the equations and then eliminate the intermediate variables to get the overall transfer function y of z divided by x of z. On the other hand, the synthesis problem is tougher than analysis problem, and synthesis problem, one of the characteristics is that if there exists one solution, then there shall exist an indefinite number of solutions. One can argue, if I get one solution, why don't I stick to it? Why do I go for alternative solutions? It turns out that different structures have different properties, and the two things that we have to worry about is overflow. That is, if at any stage in the filter there is saturation, then there shall be overflow and the filter shall cease to perform in the manner that you like it to perform. Okay? And the other problem is word length effects, that arises because of finite number of bits that you have to use, 8 or 16 or 32, and therefore of necessity the coefficients as well as the signals have to be truncated. For example, an 8-bit number multiplied by another 8-bit number gives you a 16-bit number, and if your hardware is 8-bit, then you shall have to truncate to 8 bits. Various structures have different properties with regard to word length effects, and one should choose the one which has the lowest quantization error, and this is the reason why multiplicity of structures have to be worked out before making a choice of an optimum or a near optimum structure. We also showed how to derive two structures for the transfer function P0 plus P1 Z inverse divided by 1 plus D1 Z inverse, and we showed that one can make this structure canonic with respect to multipliers as well as delays. Okay, we shall expand on this today to see how a general IIR structure, a general IIR transfer function can be realized by a canonic structure, canonic in both delays and multipliers. But before that, we start with FIR structures. No, even before FIR, let us introduce the topic of transposition. This is an important topic which allows one structure to be converted to another. The process is known as, one of the processes is transposition, and transposition can be explained with reference to this particular transfer function. And to bring variety into experience, let us change the transfer function a little bit. P0 plus P1 Z inverse, and instead of 1 plus, let us use 1 minus D1 Z inverse. Then you know that the structure that we get is x sub z summation, then Z inverse, a feedback through multiplier. It would be D1 now, not minus D1. Please be careful about this. Okay, this is why I changed it here. If it was plus, then this would have been minus D1. Okay, and then we have two multipliers, P0 and P1, which the outputs of which add together to give you y of z. This is a canonic structure, canonic in multipliers, only two multipliers, 3, P0, P1 and D1 are needed, and only one delay because it is a first order filter. Therefore, it is canonic in delays as well as multipliers. Now, in this structure, if we make the following changes, first we interchange the input and output. That is, we put the input here and the output here, x of z and y of z. Reverse all the arrows, that is, this arrow should now come like this should come like this should come like this, and so on. I will draw the total structure later, the result of this reversal. Now, as soon as you reverse, if this is also reversed, you see the summation node now becomes a pickup node. There is no summation here. A signal comes, it goes in two directions. All right. So, all summation nodes are replaced by pickup nodes, and all pickup nodes, now here there will be two signals which are coming, this one and this one. All pickup nodes are replaced by summation nodes. if you do that, then you have transposed the structure. So the transposition involves 3 steps or 4 steps. First, interchange the input and output. Okay. Reverse all the arrows, second step. Third step, replace each summer by a pickup point, just a point where signals meet, and each pickup point by a summer. And then the structure that you get, if I do this transposition to this particular structure, the structure that I get, keeping this in mind, would be something like this. You shall have y of z here and x of z here. Arrows have been reversed. X of z now is multiplied by P0 in this direction, signal flow in this direction. It is also multiplied by P1. Okay. Then from here the multiplier D1 comes in this direction. Okay. And since there are 2 signals coming, the pickup point here, P1 and D1, the pickup point should be replaced by a summer. So I get a summer, and then Z inverse is reversed in direction. So Z inverse, it goes from the summer. Okay. Then naturally we shall have a summer here, 2 signals are coming, a summer here, and the output goes here. All right. Conventionally we put the input on the left hand side and the output on the right hand side. So if I flip it over, the structure shall look like this. Capital X of Z, 2 multipliers, one is P0, the other is P1, and then I have a summer here, Z inverse, a summer here, the signal is coming on this side, the output goes to Z inverse, this is Y of Z, but Y of Z is picked up from here and the multiplier D1. Does that complete the diagram? Yes. Okay. Now if I want to find the transfer function, we have to show that this structure gives the same transfer function. You see that Y of Z is equal to P0 x sub z, P0 x sub z plus Z inverse of P1 x sub z plus D1 y of z. Correct? And if I take this term to the left hand side, then I get y of z 1 minus D1 z inverse is equal to x sub z multiplied by P0 plus P1 z inverse from this term, P1 z inverse. And you see that y of z divided by x sub z is the same that we started with, P0 plus P1 z inverse 1 minus D1 z inverse. And this is in general true. Given any digital filter structure, you can always make a transposition to get an alternative structure. The properties, overflow and word length effects are different. Ideally, if we had infinite bit arithmetic and infinite storage capacity, then the structures would have been the same. in theory they would have been the same, but in practical implementation they have different properties, and therefore it is worthwhile to determine transposed structures. We shall illustrate, we shall give one or two more illustrations of transposed structures, but but before that let us study systematically how first FIR filters are realized, and then we shall go to IIR filters. FIR, as you know, the transfer function is of the form HK z to the minus k, k equal to 0 to, let us say, capital N. Capital N I shall use for filter order sometimes and length sometimes. So, beware, okay. You have to keep track of what it stands for. Here obviously the length is capital N plus 1, okay. And this is very straightforward. You can see that y of n is equal to summation hk x of n minus k, k going from 0 to capital N, all right. And if I derive a structure which uses these coefficients hk, incidentally, as I have always done, in order to not to write these brackets again and again, I shall use a subscripted h to show this as a function of k. Now, for a general structure you can write it. Let us do it for a specific example. Let us say capital N equal to 4, a fourth order structure. Then my transfer function h of z is equal to summation hk z to the minus k, k equal to 0 to 4. So, in order to realize this, very simple minded realization is, first you draw all the 4 delays, z inverse, z inverse, z inverse and z inverse, all the 4 delays. Then your input is here. So, the input is multiplied by h naught, then after one delay h1, so it multiplies by h1, and the 2 signals are added. All summers shall have only 2 inputs, we obey that discipline, okay. Then h2, this adds to the result, therefore we shall have another summer, h3 z to the minus 3, so we have another summer, and finally h4 z to the minus 4, and this adds to the result to give you capital Y of z. This is called a direct structure because the multipliers are obtained directly from the transfer function. No manipulation is needed. Now, if you make a transposition of this, and then a flipping over, then obviously what you should get is the following. The structure that you get is, I have an x of z. Now I write the coefficients in the reverse order, that is h4. h4 should undergo 4 delays, h4xz should undergo 4 delays. So, let us draw the delays. Z inverse, okay, h3 multiplied by xz should undergo 3 delays. So, let me add this here, then I shall have 3 delays, okay. So, 1 delay, you see the pickup points are now being replaced by summers, okay. So, h2 shall be multiplied by z to the minus 2. So, 2 more delays are needed, z inverse H4, H3, H2, then this summer shall have H2, correct, 4, 3, 2, 1, H1, and finally Z inverse H0 has no delay. So, this adds here, and the output of this is capital Y of Z. This is obtained by transposition of the previous structure. They are valid structures in their own right, but in practical implementation the properties are different. They are also sometimes known in the literature as transversal structures. Transversal structures. Earlier authors, current authors also call one of them as direct from 1, the other as direct from 2. These nomenclatures are not important for us. As long as you can obtain the structure and equivalent structure, what is 1 and what is 2 is not important. There are indirect structures also for FIR filters. For example, if capital H of Z is an odd order transfer function, odd order, then I can factorize this into one first order and a number of second order factors, okay. But then you have to take H0 common, okay. You can write this as 1 plus beta 0 Z inverse if capital N is odd, 1 plus beta 0 Z inverse, one first order factor, and then a number of second order factors. You can write this as 1 plus beta 1 k Z inverse. You understand why I brought 1 here? I have taken H0 out, so I can write, I can see the zeros very clearly from the factors themselves. Then plus beta 2k Z to the minus 2, k going from 1 to how many such factors? N minus 1 by 2, that is correct, n minus 1 by 2. If it is a fifth order, then I shall have 1 first order and 2 second order terms, 5 minus 1 by 2, okay, 4 by 2 is 2. Why can't I write this as product of only first order factors? Why not? I could do that. What would be the disadvantage in writing that? I shall get complex coefficients, because it is not guaranteed that all the zeros are real. If all zeros are real, yes, go ahead, they are all first order factors, but complex factors, complex zeros must be written together so that the coefficients are real, because we want to implement the filter in real time with real coefficients. Okay. And each of these factors can now be realized in the direct form, either direct form or its transpose, whatever form you like, and then you have to cascade them together. So, this is called a cascade realization. On the other hand, if H of Z is even, capital N is even, then all that you have is H of Z equal to k equal to 1 to n by 2 of such factors. Okay. This is obvious. Each of them now has to be realized in the transversal form, whatever structure you choose. Obviously, in implementation, I told you if there exists one synthesis solution, there are indefinite number of solutions. In implementation of cascade, when you write capital H of Z as equal to continued product of H I Z, where Hij is no more complicated than a quadratic. Okay, it's either a linear term or a quadratic term. The order of cascading is important. You can start with H1 and go up to the last one, whatever the, and then you can interchange. In cascading, the order of cascading is not important as far as the total transfer function is concerned, because H1 H2 is the same as H2 H1. Multiplication is commutative in theory, but in practice the order of cascading is important from the point of view of overflow and word length effects. So your job after finding a cascade realization is not complete. If you want to implement it, then you must study the quantization behavior and the overflow behavior of the structure. Okay? And normally what one does is the section with the lowest gain is put at the beginning. Agreed? The section with the lowest gain is put at the beginning, so that its signal output does not saturate the next components, next blocks realizing the various transfer functions. Okay. Now it may not be possible to avoid overflow, particularly in fixed point arithmetic. You know, the dynamic range of fixed point arithmetic is severely limited as compared to floating point. If that happens, if you are keen on fixed point, all the other peripheral structures or all other structures are fixed point implementation, you cannot suddenly switch to floating point. That's a very costly proposition. Then one may have to scale. In other words, suppose at the ith stage the signal that you get has exceeded the dynamic range of your storage of the accumulators. Then at the I minus 1th stage you use a scaling constant, and scaling constant is usually of the form 2 to the minus I. You can divide by half. This is not a multiplier, it is only a shift. Then the overall transfer function is realized, not the original transfer function, but you realize it to within a multiplying constant. So scaling is also an important consideration. You may have to do it. One might ask, why not do the scaling at the input? Why not do the scaling at the input or the output? Well, output, if it is permissible, you may do it, but at the input doing the scaling is prone to another disastrous effect. Can you tell me what this effect is? Noise. If the signal becomes very weak, then the noise may take over, noise corruption, and therefore your scaling has also to be done in a distributed manner, judiciously, so that you maintain a balance between overflow, signal strength, and also word length effects, that is quantization errors.
So, but accuracy will also decrease by scaling?
Accuracy of what?
Result will decrease by scaling.
Result will decrease. You see, in digital implementation we are not worried about the actual value of the number, because a digital signal processor, what is its main function? Filtering. As long as you are getting rid of the undesired frequencies and accepting the ones, digital amplification is no problem. It's simply multiplying by a power of 2. So it's either a shift, it's a shift in the proper direction. Okay? So that should not be of concern in digital implementation. That's about cascades. What about parallel implementation? Is it possible to do a parallel implementation of FIR transfer function? Parallel is usually resorted to when you wish to speed up the process. Parallel algorithm, parallel software is faster than a serial processing. Parallel processing is much faster than serial. In the FIR case, however, that does not happen. Why? Because if you have h of z equal to summation, let's say h k z to the minus k, let's say k equal to 1, 0 to let's say 7, alright, then 7 delays are needed whatever way you decompose. Parallel means what? You write this as summation hiz, so there shall be at least one hi which shall contain 7 delays, and therefore the processing time cannot be reduced by parallel implementation in FIR case. This is not true in IIR, as we shall see later. However, parallel implementation is useful in the context of multi-rate signal processing, that is interpolation and decimation. Parallel decomposition helps there, and the decomposition there is done in a particular manner, and that is called polyphase decomposition. Polyphase decomposition. We shall briefly touch upon this topic because it has become now an integral part of any programmable DSP, interpolation and decimation, and they are resorted to for various reasons, but one of the main reasons is that it reduces the hardware complexity of the structure. We shall illustrate this with reference to a particular transfer function of order 8. Let's say we have h0 plus h1z inverse plus etc. plus h8 z to the minus 8. We can decompose this transfer function in various ways. We can write this as h0. Let's take the alternate terms. h2z in z to the minus 2 plus h4 plus h6 up to h8 z to the minus 8. That is only even subscripted coefficients, and then we can take h1 z inverse plus h3 z to the minus 3 up to h7 z to the minus 7. Obviously, I can write this as E0 z squared, because the power of z here is minus 2, minus 4, minus 6, minus 8. It's the power of z squared, plus if I take z inverse out of this, I get another polynomial in z squared, and therefore I can write this as E1 z squared, and obviously the implementation would be that I have two paths. One is E0 z squared and the other is E1 z squared. This is delayed by one sample and then added to give you the output. Two parallel paths, but as I said, they do not reduce the speed. I'm sorry, they do not increase the speed. Okay, they do not help in making the processor faster. However, you know that if I have a factor of 2 interpolation, then the z transform, in the z transform it is squared, and therefore if I decimate this by a factor of 2, I can realize E0 of z and E1 of z, right? So the number of multiplications, the speed thereby increases. Okay, so this is one of the tools for interpolation and decimation for multi-rate signal processing. Now there is nothing sacred about breaking up into two transfer functions. Technically this is called a two-phase decomposition. Two-phase. I can also make three-phase like this. I can write Hz as equal to E0 z squared z cubed plus z inverse E1 z cubed plus z to the minus 2 E2 z cubed, and E0 now shall be H naught plus H3 z to the minus 3 plus H6 z to the minus 6, and that is it. I do not have an H9. E1 is H1 plus, I have taken Z inverse out, H4 z to the minus 3 plus H7 z to the minus 6, and E2 would be H2 plus H5 z to the minus 3 plus H8 z to the minus 6. And the realization is obvious. You have 3 paths and you require 2 delays, two extra delays, okay. But the total number of delays that you are using is still 8, and this path, for example, z to the minus 2 multiplied by z to the minus 6 is still 8 delays are needed, okay. And now you can also appreciate that the total number of delays required in the implementation of a polyphase decomposition is much greater, isn't that right? Is much greater than in direct realization, direct or cascade realization. However, the number of delays can still be kept at 8 for this structure by sharing delays, okay. And I shall draw this, I shall illustrate this with reference to this particular decomposition. This is a 3-phase decomposition, do not confuse with 3-phase power, okay, 3-phase decomposition. I shall illustrate this with reference to this particular example, that is 8th order example. And the trick to obtain a realization in which no more than 8 delays are used is to share the delays, and we shall have, let us have 3 delays here and 3 delays here. Z to the minus 3 I have drawn in a single block, but it is 3 blocks cascaded to each other. From here I first combine signals to obtain E0, E1 and E2, okay. For example, for E0 I shall have to take an H0 multiplier, then this I have to multiply by H3 z to the minus 3, and this I multiply by H6 z to the minus 6, then I shall have to combine this, okay. So I combine these two, then I combine this, and the transfer function here, if this signal is 1, then this will be E0 z cubed, all right. Next I construct E1. For E1 I shall have to multiply by H1, well I should have done it other way, but does not matter. H1, then this will be multiplied by H2, no, not H2, H4, and I combine these two, then this will be multiplied by H7 and combined. So the transfer function that I get here is E1 z cubed. Then I have to, the figure is becoming a little complicated, but let us do it. This has to be multiplied by H2 combined with H5, then combined with H8, and the transfer function that I get here is E2 z cubed. Now, well, let me continue on the next one. I have E2 z cubed, then E1 z cubed and E0 z cubed. I have to combine them. Okay. Now E2 z cubed goes through two delays. So first delay I put it here. E1 goes through one delay only. So I combine E2 z cubed with E2 z cubed z inverse with E1 z cubed. Then I use another z inverse. All right. Then I have made sure that E1 z cubed multiplied by z inverse, E2 z cubed multiplied by z to the minus 2, then it combines with E0 z cubed to give you the output, which is h of z. Okay. This is a trick that one can employ to make this structure still canonic. All right. Any question on this? In general, if your transfer function, now you see I am using a length capital M. In general, if you have a transfer function h naught plus h1 z inverse plus etc. plus h m minus 1 z to the m minus 1, I shall go back and forth between this order and length, so that you be careful. What the length here is capital M, okay, m minus 1, and you make an L phase decomposition. Then your transfer function h of z shall be of the form z to the minus m e m z to the,
So it would be z raised to minus m minus 1.
no, minus m. You see the multipliers are z inverse, z to the minus 2, z to the minus 3. So m will go from 0 to no m by L, integer part of this. There is no guarantee that m shall be divisible by L. It will be integer part. Integer part is usually denoted like this, integer part of m by L. Then z to the power, for a three phase decomposition we had E0 z cubed, z to the power L, where m by L, this is the integer part, and hn obviously shall be 0 for n greater than equal to m. Some of them may not have the same number of components as others, because hn 0 is equal to 0 for n greater than equal to m. I do not have any other term. So this is the general L phase decomposition of a length m FIR filter. Now obviously, if the FIR was linear phase, then the number of multipliers can be reduced approximately by half. If the length is even, then because of symmetry and anti-symmetry, the number of multipliers can be reduced to n by 2. If capital N is odd, you require n plus 1 divided by 2 multipliers. Okay, and the discipline that we follow to draw the structure is as follows. I shall illustrate with this n is length or order? Length. Length, that means there are capital N number of coefficients and capital N is even, therefore we require only capital N by 2 multipliers. We shall illustrate the structures with reference to two examples. Let us say capital N equal to 7, that is H of Z equal to H naught plus H1 Z inverse plus etc. plus what will be the last term? 6 Z to the minus 6, which I can write as, to draw the structure it would be advisable to write the complete transfer function H naught plus H1 Z inverse plus H2 Z to the minus 2 plus H3 Z to the minus 3. This is the symmetry point. Okay. Then H4 shall be the same as H2 Z to the minus 4. H5 shall be the same as H1 Z to the minus 5 and H6 shall be the same as H0. Okay. So, the trick is first to obtain the required number of delays, then combine the undelayed term with the 6 delayed term, combine them in a summer, then multiply by H0. So, the structure would be like this. What we do is we first draw all the delays. We require only 6 delays. So, Z inverse, Z inverse, Z inverse 3, then we draw the other 3 in a reverse diagram. Okay. So, Z inverse, Z inverse, Z inverse. Okay. So, what we do is the undelayed term is now combined with 6 delayed term added. We have added 1 to Z to the minus 6, then the output is being multiplied by H naught and you have to add it to other terms. Similarly, H1 Z inverse is to be combined with Z to the minus 5. So, 3 plus 2 5 right here, you combine with this, then take the output of this, multiply by H1 and combine 2 signals at a time. Okay. Similarly, this shall be combined with this signal multiplied by H2 added. Okay. And what else do I need? Only H3. H3 Z to the minus 3 is available here. Therefore, you multiply this by H3 and add. So, this is your output. Okay. So, the total number of multipliers is H1, 2, 3, 4. This is 7 plus 1 divided by 4 divided by 2, that is equal to 4. It is canonic in delays. So, the total, this is also an advantage of linear phase filters. Not only they give constant group delay, the hardware requirement is lower. Okay. On the other hand, if capital N was equal to 8, let us say, that is we go H naught plus H1 Z inverse plus H2 Z to the minus 2 plus H3 Z to the minus 3, then what is the highest? Highest term is Z to the minus 7. So, it will come H naught Z to the minus 7 h1 z to the minus 6, h2 z to the minus 5 plus h3 z to the minus 4. Now what we do is we draw the delays in a different fashion. There are 7 delays, so we draw 3 of them here, and 3 of them here. I will show the arrows a little later. 1 extra we draw here. Okay, so 7 delays, right? Now we combine the same manner. Let me use a different color. Same manner, we combine this with this, multiply by h naught. We combine this with this, multiply by h1, then this with this, multiply by h2. No, this is a summer. Multiply by h2, combine this with this, multiply by h3, and then add all of them together. That's it. Now it shows not only the hardware structure, it also shows the software structure, how to write the program. The diagram will indicate to you the successive steps in the algorithm, and therefore this discipline is important. What do you think its transpose shall be? I shall leave you with that question. Transpose of FIR, linear phase structures. Will they be identical to the previous one? No? Try it out. We will stop here today.